We are very happy to have with us today Professor Benjamin Schlein. So Benjamin received his PhD from ETH Zurich in 2002. He then held positions at the Courant Institute, Stanford University, Harvard University, UC Davis, LMU Munich, and at the University of Cambridge. After that, he has been appointed Hausdorff Chair in Bonn in 2010. Since 2014, he is a professor at the University of Zurich. Benjamin is a leading figure in mathematical physics, internationally recognized for his foundational contribution to the analysis of quantum many-body systems and random matrices. He has received major international recognitions, for example, the Leroy Steele Prize for seminal contribution to research from the American Mathematical Society. He also received the Tullio Levi-Civita Prize for Mathematical and Mechanical Sciences, the Sofia Kovalevskaya Award from the Humboldt Foundation, 2 ERC grants, among many other recognitions. Moreover, he was an invited speaker at the International Congress of Mathematicians in 2018. So we are delighted to have Benjamin here with us today. He will present a colloquium with the title Bogoliubov Theory for Dilute Bose gases. So thank you very much, Benjamin, for coming.
Thank you very much for the kind invitation, and thank you very much for the kind introduction. Yes, as Chiara was saying, I would like to discuss some recent and less recent result concerning a rigorous version of Bogoliubov theory and its application to the study of the equilibrium and dynamical properties of dilute quantum gases. And all I'm going to talk about is based on a series of joint works, and these are my collaborators, Giulia Basti, Chiara Boccato, who is here, Christian Brennecke, Maurice Brooks, Cristina Caraci, Serena Cenatiempo, Jacob Oldenburg, Alessandro Olgiati, Diane Saint-Aubin, and Severin Schrave. Okay, so I'm going to focus here on dilute Bose gases, which have been very fashionable in physics in the last 30 years, since the first experimental realization in labs at MIT and at Boulder, Colorado, which led to the Nobel Prize in 2001 to Cornell, Wiman, and Ketterle. So here you see one of the first pictures coming out of these experiments. You see a picture of a momentum distribution of the particles in a gas at very low temperatures in the regimes of nano-Kelvin. And here you see 3 different pictures at 3 different temperatures. And what you notice is that if the temperature is small enough, so in this direction here, then there is a macroscopic number of particles, so a positive fraction of the particles, which are all described by the zero momentum one particle state. So all of them, they will have a momentum equal to 0, so they all condensate in this one particle state with 0 momentum. So that's the idea of Bose-Einstein condensation. And I'm, of course, a mathematician, so the goal of this talk, and more generally of my research, is to try to understand the properties of this kind of system, of this cold Bose gases, starting from first principle many-body quantum mechanics, starting from a microscopic description of a gas in terms of its elementary components, in terms of the atoms already. Okay, so since I'm not sure what is your background in many-body quantum mechanics, I would like to briefly recall some of the main postulates before we focus then on this type of dilute quantum gases. So we are going to consider systems with many particles. The number of particles will be denoted by n, and we're always thinking of n as being a large parameter. We always consider the limit where n is very large. And if you have a system of n particles in quantum mechanics, then you can describe it by means of a square integrable wave function. I call it psi n. Psi n is a function on the configuration space, so we think of our particle as moving in some domain lambda in R3, and later we will focus on a box or on a torus. And you take n copies of them because we have n particles, and then you take complex valued square integrable function on this configuration space lambda to Vn. So in particular, one of the most important postulates of quantum mechanics is that if you have indistinguishable particles, right, you cannot distinguish the one from the other, then you are not allowed to take arbitrary wave function. You are only allowed to take wave function with a certain symmetry, with certain statistics with respect to permutation of the particles. Now, in nature, there are two types of particles, fermions and bosons, behaving differently with respect to permutations. Bosonic systems are described by functions that are symmetric with respect to permutation. Fermionic systems instead are described by wave functions that are antisymmetric with respect to permutation. And in this talk, I'm only going to focus on bosonic systems, on Bose gases, and therefore I will always assume the wave function that I'm going to consider to be symmetric with respect to arbitrary permutation of the n particles. Good. Now, what is the physical interpretation of the wave function? Well, the first interpretation is that if you take the absolute value squared of the wave function, so this thing here, this gives you the probability density for finding particle 1 close to x1, particle 2 close to x2, and so on. Okay, so in particular, you see, you want the L2 norm to be normalized to be 1, because the probability that the particles are anywhere in space should be equal to 1. Okay, so that's the first thing, the first answer if you ask what is the probability, the interpretation of the wave function. But in fact, the wave function does not only contain information about the distribution of a particle in space, it contains information, it allows you to make prediction about measurement of arbitrary observable in the system. Now, in quantum mechanics, observable are self-adjoint operators acting on the Hilbert space of the wave functions. And if you have a self-adjoint operator A, so an observable A, then its expectation in the state psi n, the value that you expect to measure if you do a measurement of observable A, is just the L2 scalar product between psi n and A of psi n. So this is why using the same wave function, you can make predictions about all possible observables. For example, the momentum of a particle is going to be the derivative, the gradient in the direction of, if you want to know the momentum of the particle x1, is going to be the gradient in the direction of x1, you see? So the fact that the same wave function has information about the position, but also the momentum, is the reason why you have this kind of strange quantum mechanical effects like the Heisenberg principle, right? If you know very well what is the position, then you cannot know what is the momentum, and vice versa. Okay. Now, a very important observable in quantum mechanics is the Hamilton operator, which is the self-adjoint operator associated with the energy of the system. The Hamilton operator, at least in this talk, will typically have this form here, right? We have n particles, so we have a sum of n terms, each one acting only on one particle, of the Laplace. The Laplace is the kinetic energy of the particle. I told you the momentum is the gradient, so right from classical mechanics, you know the kinetic energy is p squared. Well, this translates in quantum mechanics into the Laplacian. Okay, so this is the kinetic energy. So this is some external potential which acts in the same way on all n particles in the system. And then, very importantly, there is a second term in this Hamiltonian here, which is now a sum over pairs, right? This one is a sum of one particle operator which only acts on a single particle. This guy here on the other hand is an interaction, so it has to act at the same time on two particles. It's a two-body interaction. In principle, you could also ask, well, what happens if you have three-body interaction, four-body interaction, but we will forget this. We will focus only on the simplest case of two-body interaction. It's already difficult, challenging enough. Okay, and it's going to be an operator, a self-adjoint operator on the Hilbert space. You see now this S appears, which means it's the subspace of L2 consisting of a function that have the correct symmetry, this permutation symmetry that I was telling you about. So why is the Hamilton operator important? Well, the Hamilton operator is important because it generates, via the Schrödinger equation, it generates the evolution of the system. So to know the system at time t, you have to solve this differential equation here, which means you have to apply the unitary group generated by Hn on the initial datum. In particular, this means that the Hamilton operator describes, the eigenvectors of the Hamilton operator are the stationary states in the system, right? So in other words, the Hamilton operator describes the dynamics, but also the equilibrium properties of the system. In particular, if you are at a low temperature, at low energy, right, then you are going to be interested in the spectral distribution, in the spectrum of this self-adjoint operator here, close to the lowest eigenvalue. Right? In physics, the lowest eigenvalue of an operator is known as the ground state energy, and then you would like to know, well, what is the ground state energy? What can we say about the ground state vector? What can we say about the excitation, about the excited eigenvalue which are above the ground state energy, but if you are at least at low temperature, you're particularly interested in the distribution of eigenvalue which are not too high, sufficiently close to the ground state energy. And that's kind of what I'm going to focus in the next slides. Okay, so that's the rough and very quick recall of postulates of many-body quantum mechanics. Let's now try to focus on this kind of system that we had this picture on the first slide, like this kind of dilute Bose gases. I'm going to describe dilute Bose gases in the so-called Gross-Pitayevsky regime, which means the following. We are going to consider n particles, so n bosons, which are trapped in a volume of order 1 and interact through a potential whose effective range is of the order 1 over n. Okay, so there is this scaling going on here. So we're going to consider the simplest possible situation. We're going to choose this translation invariant setting, which means I'm going to put my particles in a torus with size 1. So this is lambda, is this torus. You can think of it as a box with periodic boundary condition. And these are the n particles moving in this box. And then you see the range of interaction, 1 over n, is much smaller in this regime than the typical distance between particles. Right? Because in 3 dimensions, if you have n particles in a volume of order 1, the typical distance between the particles is going to be n to the minus 1/3. Right? And here the interaction only acts if the distance is of the order 1 over n, which is much smaller than 1 over n to the 1/3, because as I told you at the beginning, n is going to be a large parameter. N is going to go to infinity in my mind. Okay? Good. Now, the fact that the range of interaction is much smaller than the typical distance between the particles means that we are looking at a very dilute gas. Okay? The density is very small in this sense. Okay. Now, the Hamilton operator to describe such a system, I wrote it down here, right? We don't need the external potential. The external potential is just the trap, so this periodic boundary condition that we impose, and on this torus lambda, we consider the sum of the n Laplacian. This is the kinetic energy of the particle, and this is the two-body potential, the interaction between the particle. And you see that I'm scaling the two-body potential with n, and I'm scaling it to make sure that the effective range of the interaction is exactly of the order 1 over n, as I was telling you before. Okay? Good. Now, this function v, this potential v, in the following, we are going to assume it to be repulsive, so it's going to be positive to avoid any problem of stability, and also because our techniques do not really work if the potential has some negative part, but this is a different question. We are going to assume it is radial, and it has a compact support. Okay? Compact support means that particle I interact with particle J, so if and only if this difference here is of the order 1 over n, right? Because you want to kill this factor n here, so they only see each other, they only talk to each other if the distance is smaller than constant divided by n, if the support is compact. Good. Now I was telling you that I'm choosing the scaling so that the effective range is of the order 1 over n. I explained to you why you need the n here. Let's focus a little bit on this factor n squared here, which is important. If you don't put any n squared here, that this potential here is too soft, is too small, it will not have any effect. The particles behave as if they were free. Right? You need something here. And you need this n squared here in order to make sure that the scattering length of interaction, which is a physical quantity measuring the effective range of interaction, is indeed of the order 1 over n. Let me recall, since it will play an important role in the following, let me recall the definition of scattering length. I wrote it down here. The scattering length is defined by means of this zero energy scattering equation. This is an equation on R3 now, on the full R3, the space. It's a one-body equation, so we only have a three-dimensional Laplacian plus 1/2 v acting on f should be equal to 0, and we want to impose the boundary condition that f goes to 1 at infinity. Okay? Now, if you choose, as I told you to do, the potential to have a compact support, as soon as you are outside of the support of a potential, this guy here is 0, so we are looking for solution of Laplace f equal to 0 with this boundary condition here. Well, you know that the solution must be 1 minus some constant divided by x. This constant here is exactly what is called the scattering length of the potential v. Okay? It described how much the repulsion is effective, I mean, on which scale particles start to feel the repulsion with the other particles in the system. It's an equivalent characterization. It's easy to check. If you integrate the solution of this equation against the potential v, we will get this quantity 8 pi a. I wrote this formula because it will be useful in one of the next slides. So this is the scattering length of v, but now we want to rescale v. You remember in the Hamilton operator, the potential was not v of x, it was n squared v of nx. However, if you know what is the solution of this equation, it's very easy to find the solution of this equation here. You just have to rescale the function f. You multiply the argument with n, and then you see when you take the Laplacian, you get n squared from the second derivative, which cancels this n squared here. So this is the same equation as this one here. Okay? In particular, you see, by plugging here nx in this formula here, the scattering length of this rescaled potential is exactly a, so the scattering length of v, divided by n, which is what we wanted, right? We wanted the scattering length to scale as 1 over n, proportional to 1 over n. I tried here to draw a small picture. You see this first one thing, the small thing here is the potential v, right? And then we have the corresponding solution here of the scattering equation f of x. And then we scale it, of course, here n is like 2 or 3, but at the end it will be very large. So when you scale the potential, it becomes, the support gets smaller and the size gets larger because of this n squared factor. And accordingly, the solution of this scattering equation will concentrate close to 1, right? Because the scattering language tells you on which scale this guy bends down from 1 is going to be a over n for this guy here. Okay, so that's the scattering length. Okay, now let me mention a couple of, by now, say, classical results concerning the spectral properties of the Hamilton operator I had in the previous slide. So this Hamilton operator describing this n-particle Bose gas in the Gross-Pitayevsky regime. So the first rigorous result, say, is a bound for the ground state energy. Remember, the ground state energy is the lowest eigenvalue of this self-adjoint operator, which goes back to the work of Lieb and Ingvason already in 1998. And what they proved is they proved that to leading order, the ground state energy is given by 4 pi a times n, times the number of particles, plus an error which is of smaller order. It goes to 0 if you divide it by n. Okay? As n goes to infinity, of course. Okay, so the first maybe important remark here, and that's the reason why I introduced the scattering length. You see the importance of the scattering length already here. To first order, the energy only depends on the interaction potential through the scattering length A. It does not matter what is the precise profile of your potential. The only thing which is important here, the only thing that you see in this formula is the scattering length of the potential. Okay? Good. Now, there is another important result a couple of years later by Lieb and Zeilinger. So this result describes the ground state vector, so the eigenvector associated with this ground state energy En. Okay? And it shows that the ground state vector exhibits Bose-Einstein condensation. So let me try to explain what this means. Right in the picture I told you, Bose-Einstein condensation means that you have a macroscopic fraction of a particle all in the same one particle state. But how can you express it mathematically? And this is the right way to express it. What we proved is that if you have a wave function psi n with energy, expectation of the energy, close enough to the ground state energy, to this En here, right? And that's certainly correct for the ground state vector, right? It's not only correct for the ground state vector, you can have what are called approximate ground state vectors, state whose energy is sufficiently close to this ground state energy. Then you can look at the one particle reduced density associated with psi n, which means you integrate out the degrees of freedom of n minus 1 particle to focus on a single particle. In the language of probability theory, here I'm taking the marginal distribution, right? Quantum mechanics, the probability is quadratic in the psi, so it's a little bit more complicated. You have to do it using this one particle density matrix gamma n, but it's the same thing. And then what we prove is that if you take this gamma n here, the one associated with psi n having sufficiently low energy, then the expectation of this psi n in the zero momentum state phi 0, so phi 0 is just the constant, is the state with zero momentum on our torus. This converges to 1 as n goes to infinity. Okay? So the scaling of the normalization of psi n is an operator with trace equal to 1. The fact that you can find phi 0 having this thing here means that almost all particle up to a fraction which goes to 0 as n goes to infinity must be, can be described as being in this one particle state phi 0. Okay, so in this case, condensation is even complete, right? So almost all particles are in the same one particle state phi 0. I put a warning here. I wanted to stress you that this does not mean that psi n is well approximated by the product of n copies of phi 0. Okay? Because you can take, if you took psi n to be this very simple factorized function, it's very easy to compute what is the energy, right? Because, well, phi 0 is 1. So here I wrote phi 0 to the n, but I could not just have wrote 1. The kinetic energy for 1 is equal to 0, so you only get a contribution from the potential energy, right? You have to integrate the potential v of x, you get v hat of 0, and if you count how many particles you have, that multiplies a factor n over 2, okay? And now you remember I told you what is this characterization here with scattering length. You see f is smaller than 1, so you see immediately that 8 pi a is strictly smaller than the integral of v, which is v hat of 0. 8 pi a is strictly smaller than v hat of 0. It means this energy here is larger than what we know to be the ground state energy. But it's not just larger by a little bit. It's larger by a factor n, because you have a wrong number and you multiply with n. So you are very far energetically from the ground state if you consider the factorized wave function. So having condensation does not mean that you are close to a factorized wave function. That I wanted to stress. Right? And the point is that correlations between the particles are crucial, and they are responsible for pulling down the energy from this number to this number here. And when you take the marginal, you integrate out the correlations, and then you can prove condensation like that, but not at the level of the wave function, only at the level of the marginal distribution, only at the level of the reduced density. Okay. So these are the sort of classical results. Now let me mention some of our a little bit more recent result. So this is the first one that I would like to mention, together with Chiara, with Christian Brenneck, and with Serena Cenatiempo, goes already back almost 10 years, 9 years. Okay, so what we prove here is an improvement of the result of Lieben, Saringer, and Ingwerson, if you look at it, right? So the first bound is a better bound for the ground state energy. You remember that Lieben and Ingwerson proved that En is equal to 4 pi An plus something of smaller order, and what we can prove here is that indeed the smaller order remains bounded as n goes to infinity. Okay, so this is the correct energy up to an error which is bounded by a constant, okay, uniformly in n. Good. So that's the first one, and this is an improvement of the condensation bound. The setting is like before, right? We take a wave function psi n normalized, and we assume that the energy is close enough to the ground state energy of the system. Then we can show that this expectation here, right, not only converges to 1, it converges to 1 with rate 1 over n, okay? So this means that the fraction, I mean, if you have n particles, right, most of them are in the condensate, right, the fraction which is not in the condensate is of the order 1 over n. So the number of excitation of the condensate remains bounded as n goes to infinity, in other words. Okay, so these are just stronger estimate, but in the same spirit of the bounds of Lieb and Ingvason and Lieb and Saringer in the previous slide. Okay. Now, if you look at this bound here, of course, the next natural question is, what can we say about this C here, right? Of course, I mean, it's interesting to have a better approximation of the ground state energy, but if you can resolve the order 1 energy, that's important because then you also start to see the excitation of the ground state, right? So the spectrum starts at order n. The first eigenvalue is a constant in 4 pi a times n, but then the excitations, the distance between excitation is much smaller, it's order 1. Right? So if you want to say something not only about the ground state, but also about the excitation, you must be able to resolve the order 1 energy. So that's the next result here, 2018. So this is a better bound for the ground state energy. En, the lowest eigenvalue of the Hamilton operator that we had in the first or the second slide in this talk. So you see again this factor 4 pi a times n that we already had before, but now we also have, this is the order 1 contribution, this strange constant E lambda times E square, which is given by this series here, and then there is this sum here. It's a sum of the momenta, right? We are on the torus, so momenta are discrete, momenta, the p's are always chosen in 2 pi z3. And the plus means that we exclude the zero momentum. Okay? Good. Now, if you look at this sum here, you may be worried that it does not converge as p goes to infinity, but if you expand this square root, you will see that you will cancel all 3 terms here. So this summand here is of the order 1 over p to the 4, which is summable in 3 dimensions. In other words, this is a number of order 1. Does not depend on n. Okay? And then there are correction errors, which are of the order n to the minus 1/4. They go to 0 as n goes to infinity. Okay? So that's the new improved estimate for the ground state energy, which also resolves the second order part. Now I have a comment here about the emergence of this E lambda A square, which is a bit strange. This factor is due to the fact that we defined the scattering length A by looking at this scattering equation on R3, right? But now we are not on R3, we are on this torus, right? And of course, the scattering takes place on distances of order 1 over n, so the difference, it does not matter that much that you are in the torus and not on the full space R3, but at this level of precision, it does matter, and it creates this additional correction here. Okay, so this is about the ground state energy, but as I promised to you, if you can resolve the order 1 energy, then you can also say something about the excitation spectrum, and this is this next theorem here. So we consider the Hamilton operator Hn like before. Now we subtract the ground state energy En, right? The spectrum of this guy, by definition, starts from 0. 0 is the first eigenvalue. But then we want to see what are the other eigenvalue below some threshold zeta. And then the result is that the eigenvalues of this guy here below a fixed threshold zeta, they have this form here. They are given by the sum of momenta of some integer np. So the important restriction here is that np must be an integer, 0, 1, 2, 3, and so on. And times this square root here, again, up to corrections which goes to 0 as n goes to infinity. Okay, so the interpretation is very simple. If you want to build up the spectrum of this operator, at least close to the ground state, you have to tell me for every p how many excitations you want with momentum p, and each one of these excitations costs us this energy here, and then you compute the full energy, it's just the sum over all the p. Okay? Since you want to stay below this threshold zeta, you can only have a finite number of p with np different than 0. Okay? So this is in physics, they call it a quasi-particle interpretation. So the excitations are thought as particles having a certain energy, and that's how you build the spectrum. Good. Now I should mention that there were similar results to these bounds here in other type of regime, mostly mean field type of regimes, which are mathematically a little bit easier to handle, because in that situation, every particles interact with everybody else, and the math is a little bit simpler. Good. Okay, so then maybe, so this is 2018, so maybe something more recent. Recently, in a joint work with Cristina Caraci, Alessandro Olgiati, and Diane Santoben, we were able to get even to the next order in the expansion for the ground state energy. If you look at the first two lines, this was the theorem that I mentioned before. Now the next order correction, remember, the first term is order n, then this line here is order 1, and also this correction here is order 1, and then the next order is of the order log n, sorry, the next correction is of the order log n over n. Okay, so now we can identify also this correction here. The even next order term is expected to be of the order 1 over n, and it is expected to be not universal anymore. You see, so far, up to here, you only see the scattering length. Everything only depends on the scattering length up to here. It's only on the next order, the order 1 over n, which you start to see other quantity characterizing depending on the interaction potential. Up to this log n over n, only the scattering length matters. Okay, good. Now let me also mention some extension and some related result. I didn't make you pay attention on it, but if you go back to all this theorem, for example, this one, so we derived all this theorem under the assumption that the potential have some integrability, satisfies some integrability condition. So here it's in L3, and I think also the other theorem were written with V in L3. Probably pushing this method, you can go a little bit better. You can do L2, maybe you can even do L1, I don't know. But certainly you need some integrability. You need the potential to be integrable, right? It cannot be too singular. In particular, these theorems here did not apply to the case of hard sphere. Hard spheres means that your potential is infinity if x is smaller than a, and 0 outside of this hard core. Okay? So in the case of hard sphere potential, the scattering length, of course, coincides with the radius of the potential. Okay. So instead of taking this potential to be infinity, you can redefine the hard sphere ground state energy by looking only at the kinetic energy, no potential, but you impose a boundary condition, x a boundary condition, asking that the wave function is equal to 0 whenever two particles are at distances smaller or equal than a over n. Right? Of course, we are still in the Gross-Pitayevsky regime, so the scattering line must be of the order 1 over n, and that's why here the natural quantity is exactly a over n. Okay, and then you would like to get some estimate for this hard sphere ground state energy. The most challenging part to get bounds on this thing here is not the lower bound, it's the upper bound. Because for the lower bound, well, you can imagine that you can sort of approximate this hard sphere with something which is not an hard sphere, and then you can try to apply methods which are more or less the same as in the previous theorem, or later we will discuss some other situation where methods have been developed to handle the lower bound for hard sphere. The upper bound was the most challenging part, and that's what we established in this work with Giulia, Serena, Alessandro Olgiati, and Giulio Pasqualetti a couple of years ago. You see that the energy, at least to this second order precision, so here we don't have the third order yet, although probably one could also get there, but the formula is exactly the same as for the integrable potential. Okay, so we are still in this universality, in the same universality class. All the energy, also for our sphere, only depends on the scattering length, not on the profile of the interaction. Good. So that's the first remark. The second remark is, well, you can ask what happens if instead of putting your particles in this torus, right, you let them move in R3, but you confine them with an external potential, right? For example, an harmonic trap or something like that. So in this case, the Hamilton operator, I wrote it down here, now it acts on R3 or R3n, but it has a new external potential term, which is this guy here. The interaction is the same as before. The novelty is this external potential here. Right? In this case, now let's go back for a second to the classical result, or the Lieb, Saringer, and Ingersoll result. Well, what they proved in this case is that the ground state energy per particle to leading order is given by the minimum of the so-called Gross-Pitayevsky energy functional, which is this nonlinear functional that I wrote down here. Okay? You see, if you are in the case of the torus, right, then you have to choose phi equal to 1, this goes away, this is not away, and you recover this 4 pi a times n that we had in the previous slide. So this just extends the result for the torus to general trapping potential. Good. Okay. And Liebensaringer also proved that you have condensation in the same sense as we had above. Of course, now condensation is not going to be in the zero momentum state, right? Where do particles want to be to minimize the energy? They want to occupy the minimizer of this functional here, right? So in first approximation, most of the particles are going to be described by the phi minimizing this functional here. And this I call phi GP, okay? The minimizer of the Gross-Pitayevsky function. Okay, so these are the leading order results, right? Leading order for the energy, leading order knowing that you have condensation. And then, of course, you can ask the same question that we did in the torus, and these are the results. So the first result is about condensation, right? If we assume that in energy we are close enough to the ground state energy of the gas, so to the leading order ground state energy, then we have condensation again with rate 1 over n. And this is the result about the spectrum, together with Christian Bernegg and Severin Schraven. At the same time, also Nam and Ernaud-Trier had a different proof of a similar result. Okay, so now to describe the ground state energy and the spectrum in this trapped case, it's a little bit more difficult because you cannot use momentum space, right? You cannot use Fourier theory because of this external potential. So instead you have to define first the operator H like that, and then with H you define this operator E, right? And then I only wrote the result about the excitation spectrum, not the one about the ground state, but because the formula are not very nice. But for the excitation spectrum, the eigenvalues of this guy here take this form here up to correction which goes to 0. And what is this form here? Ni again is an integer, and Ei are the eigenvalues of this guy here. Okay. Now, if you compare with what we had before there was no external potential, the phi GP was just 1, right, just the minimizer, so this is just p squared plus 8 pi a, and if you replace here p squared plus 8 pi a and also here, you will find the same formula that we had before, okay? It's just more complicated here because you don't have translation invariance and life is harder. Okay, but the spirit of the result is the same as before, right? Again, you have to tell me how many excitation you want of the type I, and each one of these I excitation costs us the energy Ei, which is the ith eigenvalue of this operator here. It's the same type of bound. Okay, so that's what I wanted to say about trapped gases. The next question that you can ask, of course, well, I described so far results in the Gross-Pitayevsky limit. I told you this means that the particles are in this box of size 1, interacts with through a potential with scattering of order 1 over n. But this is, of course, not the only interesting limit. If you look at the physics literature, there are probably the more familiar limit is the thermodynamic limit. So what does thermodynamic means? It means that you let the number of particles, you take n particles, you let them move into a box or a torus with side length L, and then you let n and L go to infinity, keeping the density n divided by L cubed constant, okay? And then you can ask, okay, what can we say about the energy of a system in this limit, and so on. And this is a question which has been very popular in physics, and already in the 50s there were bounds by Li Wang-Yang and then by Wu and also others, making a prediction about the ground state energy density. So you take the ground state eigenvalue, this En, right? You divide by the volume of your box, L cubed, and then you let n and L tend to infinity, keeping the density constant. As I told you, this is this so-called thermodynamic limit. And what they predicted, these guys here, well, is that in the dilute limit, so for small rho, but fixed independent of n, right? First you let n and l go to infinity, keeping the rho fixed, and then you look, okay, we get a function of rho. How can we expand this function for small rho? And what we predicted is that to first order you have this 4 pi a rho squared termed, and then you have a correction here, rho to the 1/2, actually rho to the 5/2 if you combine with this one, and the next correction is rho to the cube times log rho. Okay? Yeah? No, the interaction is 1. You have this box L, and then the size of the interaction is 1, or A. There is no 1 over n here. Okay? I mean, maybe you can do a picture. This is L. You have n particles, and each one has a potential here whose I mean, we call it A, but it is of order 1. It is independent of n in this limit. You can, exactly, you can do that. The Gross-Pitoyevsky limit after the scaling means, however, that you have to take the L equal to n. It means that the rho, the density is very small. It's 1 over n squared in the Gross-Pitoyevsky limit, you see? So you can reformulate the Gross-Pitoyevsky limit like that, but then the density is very small. It's 1 over n cubed. So in a sense, you can think of the Gross-Pitoyevsky limit as taking as diagonal limit where the density goes to 0 as n goes to infinity, like 1 over n squared. Okay, so these are the prediction by in the physics literature already in the 50s, and then of course a goal of mathematical physics in the last 70 years has been to try to make this formula rigorous, and the first rigorous result in this direction was already obtained by Dyson in 57. So Dyson was able to prove an upper bound matching this first order term is 4 pi a times rho squared. And the matching lower bound was given by Lieb and Dean was in 98. So if you combine these two works, then you know the first term, this one, rigorously. And then after proving the one, the focus shifted on the next term, the second term, the so-called Li-Wang-Yang term, because Li-Wang-Yang prediction was up to here, right? And then Wu came and also predicted the third term. So how do you get the Li-Wang-Yang term? Well, the lower bound was recently proved in papers by Fournet and Solovey. So the first paper was for integrable potential. The second one also allowed for this hard sphere case. Okay, so they developed methods also to handle lower bound for hard spheres, which would also work in the Gross-Pitoyevsky regime, but because previously I mentioned that we have an upper bound also in that regime. Okay, as for the upper bounds for the second term, the first to get the correct upper bound were Yao and Dean in 2009. More recently, together with Giulia and Serena, we got a simpler proof of the upper bound up to this order here, which extended the result of Yao and Dean to more general potential, because it was also restricted for the type of potential, but our bound was not allowing for hard spheres. And then very recently, and I talked about it in the conference yesterday, in this paper with Giulia, Morris, and Serena, and Alessandro, we extended the upper bound also to the case of hard sphere interaction. So now, if you combine this paper here with this paper here, the Li-Wang-Yang term is known also for hard sphere interaction. So up to here, we have quite a good understanding by now. And now there is the third order term, and for the third order term, we recently proved an upper bound, but the lower bound is still wide open in this thermodynamic limit. I showed to you that in the Gross-Pitoyevsky limit, in this ultra-dilute limit, we also have the lower bound for the third order term, but not in the thermodynamic limit, which is more challenging from a mathematical point of view. Okay, so that's about the thermodynamic limit. How am I doing here? Running out of time. You can also ask the same type of question from the point of view of dynamics, right? So dynamics, if you want to study the dynamics in many-body physics, it means, well, you want to study what happens when you change the external field. What is the reaction to a change of external field, right? You take your system, like in the picture at the beginning, right? You take your system, you confine with some external field, you let it relax to to the ground state if you are at zero temperature, to some equilibrium state, right? And then there is no dynamics at this point. But when you shift off or you switch off the external field, then the system starts to evolve, and you would like to describe the resulting evolution. And that's the sort of idea in this theorem here, together with Christian. So we choose initial data psi n, and we assume that we have condensation. Having condensation means that AN goes to 0, and we also require that the energy is close to the the Gross-Pitayevsky energy, right? So this corresponds to the idea we are thinking of the initial data as being the ground state of a trapped system. Okay? And we know, because of the result I mentioned before, if you look at the ground state of a trapped system, then these conditions are satisfied. Actually, they are satisfied with the rate 1/n in both cases. Okay? So that's the assumptions on the initial data, and then we study the evolution, but without the trap. You see, there is no trap here. Hn is just the Laplacian and the interaction. And this is the solution of the Schrödinger equation. And then we take the reduced one-particle density associated with the solution, and we prove, well, at time t, we still have condensation, right? If you know that at the beginning you have the rate 1/n, also at time t you still have the rate 1/n, at least for fixed t. You see that if you evolve too much, if the time is too large, then this deteriorates very, very quickly. But for fixed t, the rate is still 1/n here. But you do not have condensation in the same state as we had at the beginning, right? Because the condensate is going to evolve. And how does it evolve? It evolves according to the nonlinear Gross-Pitayevsky equation that I wrote down here. Okay, so the many-body dynamics, the linear many-body dynamics can be described in terms of this nonlinear one-particle evolution. Okay, good. Now, let me try in the last 5 or 10 minutes to give, is it okay? Okay. So to give some idea, mostly heuristic, about the proof of all this result that I mentioned. And the proof is based, as was already I told you at the beginning, on Bogoliubov theory. And it's also the title of the talk, so that's why I would like to tell you something about Bogoliubov theory. Now, to talk about Bogoliubov theory, I have to switch to a different representation of a system where the number of particles is not fixed. So instead of describing the system in the L2 of lambda to the n, right, we describe the system on this Fock space where we sum over all possible number of particles. Okay? It may seem strange that we want to consider the number of particles as not being fixed, because our system preserves the number of particles, so there is no important reason why we should let the number of particles change, but it's going to be very convenient, as I hope to be able to show you in a second. Okay, if you are on the Fock space, it's very useful and very convenient to introduce these creations and annihilations operator, AP and AP star. AP star creates a particle with momentum p, AP annihilates a particle with momentum p. Okay, I didn't write the definition, it's not very illuminating, just think of this meaning of this operator of creating or removing particles. We allow to jump from one sector with n particles to a sector with n plus 1 particle, or back to the sector with n particles. The important observation here is that we satisfy canonical commutation relation, which I wrote down here. In particular, the commutator between A and A star is 1, everything else is equal to 0. And another important observation is that if you take the product AP star AP, this operator here measures the number of particles with momentum p in the system. In particular, the total number of particles in the system is the sum over all momenta of AP star AP. Okay? Very quick introduction on this is the formalism of second quantization is called. Okay, let me rewrite the Hamilton operator in terms of these creations and annihilations operator. Right, the first term is the kinetic energy. This is, I think, believable because I told you AP star AP, this measures how many particles you have with momentum p. You multiply with p squared, that's the kinetic energy. You sum over all p, that's the total kinetic energy of the system. Okay? So the second term is the interaction. Right? Now, the interaction is a two-body interaction, so it's a two-body operator. So instead of being quadratic, it's going to be quartic in A and A star. Okay? And since the interaction is not diagonal in Fourier space, that's why it seems more complicated than the kinetic energy. But I mean, it's a simple computation to show that this is exactly equivalent to the Hamilton operator that we had in the first slide of this talk. Okay, it's just a fancy way to rewrite it if you want. But now comes Bogoliubov. And Bogoliubov knows that there is Bose-Einstein condensation in the zero momentum state. So he knows that the operators A0 and A0 star are going to play an important role, a special role. Okay? Why? Well, because A0 star times A0 is the number of particles with momentum 0, which we know to be close to n. Okay? It means that both of them should be close, at least heuristically, to square root of n, and therefore much bigger than the commutator between them. Okay? So for this reason, he said, well, if operators are so much bigger than the commutator, well, I can think of this thing just as number, forgetting the fact that they don't commute. Okay? So what he did, he took this Hamiltonian here, and whenever you see an operator A0 or A0 star, you replace it by factors of square root of n. Okay? And if you do this, you find this formula here. Now, it's a very simple computation. You see, here there is no A0 or A0 star, because if I put p equal to 0, then I multiply with 0, it goes away. But here, of course, I can choose to have all the 4 indices equal to 0. If you take all of them equal to 0, then this counts as n squared, or more precisely, if you do it correctly, n times n minus 1, which you divide by n. You have to put v hat of 0, and then you find this big contribution here. Okay? Good, then the p square is this thing here. The next contribution coming out of here, you cannot have 3 labeled to be equal to 0 and the fourth one to be different because of conservation of momentum. So if 3 of these labels are 0, also the fourth must be equal to 0. So the next possible case is when 2 of them are 0 and 2 of them are different than 0. And this gives rise to these terms here, these 3 terms here. Actually 4, there is also this one. Okay? Because of course I can choose p plus r and q to be 0, then I get this contribution here. If you choose p and q plus r to be 0, you get this guy here. And if you choose 1 star and 1 without star to be 0, you get this contribution here or this contribution here. Okay? And then of course there are also contributions where there is only one of the 4 terms where the label is 0, right? And this is already carrying a factor 1 over root n, right? Because I only have a square root of n, which with 1 over n in front goes down to 1 over square root of n. Or there are 4 labels all different than 0. And then this is a 1 over n correction, okay? And so what Bogoliubov did is, well, if you look at this formula, it looks like the third and the fourth term, they look small, because they still carry this 1 over root n or 1 over n factor here. Now there is no A0 left here, right? And since there is no A0 left, all these guys, you should think of them as being order 1, and then you can expect that these contributions are small because of these factors. Okay? So Bogoliubov said, well, let's forget about third and fourth line. Let's focus only on the first 2 lines. Because if you focus only on the first 2 lines, it's only a quadratic operator. And Bogoliubov knew how to diagonalize a quadratic operator. Okay? You can do that by means of what are now called Bogoliubov transformations. So this is a unitary transformation T, having this form here, the exponential of some quadratic expression. Okay? And the nice thing about Bogoliubov transformations is they act explicitly on creations and annihilations operator. They do this sort of symplectic rotation of these creations and annihilations operator. So you have explicit formula. Okay? So this means if you apply the T's on the Hamilton operator, or at least on the quadratic part of the Hamilton operator, right? You do it here. You have to rotate each one of these AP star, AP, and so on, right? And then you choose the coefficients eta p, exactly so that at the end the coefficients in front of the A star operator or the AA operator vanish. Okay? And if you do the right choice, at the end you end up with, well, the old constant, a new constant coming from several commutators to put things in normal order, and then only an operator of the form A star A. And I like A star A because I know the spectrum. A star A counts the number of particles. The spectrum with these guys here are just the integer. okay? 0, 1, 2, 3, and so on. It's an harmonic oscillator, okay? And they're all decoupled, right? Because you sum over different p, but for different p, this operator commute with each other, so if you know the spectrum of one of them, you know the spectrum of everything. So if you look at this formula here, you can already guess what is the spectrum of this operator Hn, right? These two lines are the ground state, and this determines the excitation spectrum. But if you compare it with the theorem, you see, well, it's not exactly the same. You see, you still have all this factor of v hat of 0, v hat of p over n. I don't see the scattering length here. And then there is a footnote in the paper of Bogoliubov where he thanks Landau, because Landau pointed out to him that v hat of 0 and here, and v hat of 0 minus this combination here, these are Born approximations for the scattering length, for 8 pi times a. So Bogoliubov, what he did is, well, he just replaced v hat of 0 by 8 pi a0, 8 pi times the scattering length a, and if you do that, you end up exactly with the right formula. Okay? This is the replacement that he did. This, you replace with this, and this is the second order Born approximation. You also replace with 8 pi a. And then you get the right answer. But of course, if you want to do it on the mathematical rigorous, if you want to do this computation mathematically rigorous, of course, you cannot just replace a number by a different number, right? So the question is, why did he get the right answer with this replacement? And the answer is, well, because he forgot about the cubic and the quartic part, right? The cubic and the quartic part, if you look closely, they are not negligible, and in fact they contribute to the energy exactly by renormalizing the potential in the quadratic and in the constant part. Okay? So the change from v hat of 0 to 8 pi a is coming from the quartic and the cubic part. So if you want to do things rigorously, you first should extract the relevant contribution from the cubic and the quartic part to renormalize the potential, and only afterwards you should apply this Bogoliubov transformation to diagonalize the operators and compute the spectrum. Okay? And that's more or less what we did, I mean, at least in some of the paper that I mentioned. Thank you very much for your attention. Thank you.
For the very nice talk. Are there questions? Yes.
Can you go back to the initial when you read the initial, like slide
16.
16?
Yeah.
A simple question. Here in
this is the dynamics.
just the third line, yeah. When you define the Newtonian here, universally you must have hidden in your net potential a scaling like 1 over n squared, right? So basically you brought out the n squared because it's community. Because I was just thinking about the extensivity property of the Newtonian, right? To guarantee extensivity.
Yes, you mean that it is the energy proportional to n.
The coupling term should be proportional to n squared.
This one, n squared here.
And that should be too extensive.
No, because you have an n here. Maybe the better way to think of it is n cubed times v of n divided by 1 over n. N cubed by v of n, think of it as approximating a delta function in the limit, and then you have n squared term because you have n squared pairs, but you still have a 1 over n in front, and that's why it's of order n, the energy at the end.
Okay, so that guarantees like scaling with n.
Yes, yes.
Although one expects physically the pairing term to scale like n squared, right?
What do you mean? No, because it depends how many particles you are close. I mean, you want to think about the Gross-Pitayevsky, then you write. I think. So look.
I'm thinking about it from like the Ginzburg-Landau potential. Like you have the kinetic term scales like n. You expect any coupling term and interaction term to scale like n squared, right?
I don't know, I'm not sure what are the models that you have in mind, but one model which is related with this one is the one with this mean field type of interaction. In the mean field case, you have the kinetic energy, which is order n, right? Then you have the potential energy, V of xi minus xj, right? And here you should think of the particles as being in a box with size 1, so everybody talks with everybody else. This is n squared, but then you put a 1 over n in front. Okay? And now if you go there, to that Hamiltonian, you just have to replace the potential V, which is now everybody talks with everybody else, with a local version of it. So I put n cubed times V of nx. Okay, and then this is exactly that scaling, because n cubed divided by n is n squared, and this is still extensive of the order n, as you see.
Okay, I think there was, yeah, okay.
So like slide 5 or 6, I forget. So you mentioned that okay, there are maybe 7. Sorry. Yeah, you mentioned that the total state is not IAD, right? It's not phi.
Exactly. Yes.
Okay. So but there is this notion of information. I think Renato read that.
Yes.
Of almost IAD or almost power states. They have different names. It works like this. So you start from an IAD state.
Yes.
And then you allow yourself to replace, let's say, in R sites. You remove the IAD state and you put some global state of those R sites. It can be anything. And then this R sites can be anywhere. You take the span of all these vectors.
Yeah.
And you intersect the fully symmetric subspace. And that gives you a set of almost IAD states with R effects out of n sides.
Yes.
And then you can take the limit when R is like sublinear again.
Yes.
So now is the psi n of this form?
So you are talking about a lattice system. You have points in the lattice, and I'm talking about a continuous system here. So it's a little bit different. I can tell you.
Like n particles, I'm saying. N particles, you remove R of this
Okay.
states, and you put any state there, any two state there.
I don't think that's the same. I mean, that's a good approximation. I mean, a good approximation is, for example, if you take a Jastrow factor, so something like 1 minus. Right, I mean, or take the solution of this zero energy scattering equation, we call it F. Right, and you should think of this as being 1 minus A over nx, something like that, plus some corrections. Right, and you take the product over all pairs of particles, xi minus xj. Right, so the dominant factor is the 1. If you take the marginal, you see the 1, and that's why you get the condensation. But these are the correlations which are important. And this change the state. So I don't know if you can approximate the effect of these correlations by means of what you say. So this is one way to do it. A different way to do it is, right, you generate correlations by means of this Bogoliubov transformation. So you take this eta p, a star p, a star minus p, minus a p, a minus p. So that's more or less what we do to make this approach rigorous, right? And then you apply this guy on the factorized state if you want, okay? So then you kill two particles and you create two particles with some amplitude. So this creates correlations, and this makes the state a better trivial state for the energy. We still not allow you to go to the right energy, but it's getting you, at least to leading order, this gets you to the correct energy, in contrast to this guy here.
Because the states are like very important because information like
yeah. Yeah, maybe they are also related, but I'm not. I should have a look at it. Yes.
Okay, I think.
If you go a couple of slides afterwards, you were talking maybe the one before.
Yes, here.
Like you have that if a state has an energy that is close enough to the leading order energy, you have that the difference or this sort of condensation estimates can be expressed with some sort of error that goes like 1 over n.
Yeah.
Is it known any like better sort of decaying precision, maybe by paying in the approximation? If I have like En minus 4 pi n, and then the second order, can I have some sort of better decay, better condensation?
No, this is optimal. In fact, you can compute how many excitations you have in the ground state. So psi ground state, and then you just measure the number of particles. I don't know. Let's put it like that: p different than 0, AP star AP, psi ground state, and then there is an explicit formula. I mean, you can. Actually, I don't remember the formula, but you can find it, and this is of order 1. So which means that there are order 1 excitations in the ground state. It's not. You cannot expect to have less than that.
Yes.
As a physicist, I may be interested in situations in which the particles have an attractive interaction.
Yes.
So if I understood correctly, instead most of the results rely on A positive.
That's correct.
Easy but instead the last Bogoliubov sketch of the argument could be applied for V0 negative.
The Bogoliubov sketch is a very non-rigorous argument.
What does go wrong?
Okay, so first of all, you can ask different things, right? I assume the potential to be pointwise positive, so v of x is bigger or equal than 0 everywhere. Now, first question that you can ask is if you have a potential v of x which is mostly positive, but it has some negative parts. Something like that, maybe. Okay? And the scattering line is still positive, right? Then the expectation is that everything works in the same way. Our techniques are not good enough in order to capture this thing here, but the expectation is everything is the same. If instead you have a really negative scattering length, then you have problem of stability, right? Then probably the ground state is going to be minus infinity, so this bounds cannot be true, but you can still ask some question. For example, from the dynamical point of view, you can start with some kind of condensate and evolve it with something which has a negative scattering length, and you should still be able to find something like that with a Gross-Pitagevsky equation with a negative, with an attractive coupling this time. But this is out of the scope. I mean, we cannot do it. You see, when you do the analysis rigorously, you create a lot of error terms, and to control all these error terms, the positivity of potential is crucial. I mean, so it would be much more difficult to do it for a negative potential.
So there are no rigorous results on how you have this instability that for me maybe this transition towards super solid.
Yes.
When you have the Eurocon spectrum.
We don't have rigorous result in that direction. Maybe there is something in this case here where the A is still positive, but there is some negative part of the potential, and this you can probably get the first order approximation to the ground state energy, but not for the real A negative case.
Thank you very much.
Thank you.
Are there other questions? Okay. If not, we thank Benjamin again. And we have a coffee break upstairs in the first floor, so you're all